Hello student, today we are going to see the video which will explain you to find the shortest path from a specific node to all other nodes using Dijikstras algorithm. So we are going to study Dijikstras algorithm with this particular video. The main objective, learning objectives of the video is as after watching the video, student will be able to understand Dijikstra's algorithm. Student will be able to define hop, or you may also call it as a cost. Students will be able to define adjacent node, far away node, what is the shortest path, how to consider the distance or hop count at the initial phase of the Dijikstra's algorithm. Then students will be able to describe the iterations. So this is the given example where we have to find the shortest path from node 1 to all other nodes using Dijikstra's algorithm. So let us see first of all what is hop. Actually in this video, whatever the in this example, whatever the circled numbers represents the node number, node 1, node 2, node 3, node 4. Now the numbers which are present on the line represents the hop count or distance from previous node to the next node. This hop count may be in terms of a delay, maybe in terms of a bandwidth, or maybe in terms of a distance need to travel from node 1 to node 3. For example, this is the 2, hop count 2. So this is nothing but the hop count. Every hop count has been represented on the branches. Now this can also be called as a cost. Hop count can also be called as a cost. Now we'll see node 2 and node 3 are directly attached to node 1. So these are the adjacent node. Node 3, node 2, node 4 are adjacent node to the node 1 since they are directly connected. But node 5 and node 6 are far away. Those are not directly connected to node 1. That's why those are called as a far away node. The hop count of the adjacent node is represented by the number which is present on the connecting line of the node 1 to node 2. For example, hop count for node 2 is 3, whereas the far away node hop count is normally represented by infinity. So let us see how to solve this problem with the help of Dijikstra's algorithm. To solve this problem, we have to create a tabular form in this way, where the first column will be the iterations, second column is the nodes which have been added in these iterations, and the next columns are nothing but the remaining nodes to which the distance has to be found from the previous node, first node. Here we have to find the distance from node 1 to remaining all nodes. So D2, D3, D4, D5 and D6 are the nodes which are remaining. So first iteration is always the iteration where the which contains the node from which we have to find the distance. So here we have to find distance from node 1 to all other nodes. So first iteration consists of node 1 only. Now node 1 is directly connected to node 2 with the hop count 3. So that hop count has been replaced over here. Node 3 as well as node 4 have been directly connected with the hop count 2 and hop count 5. So it has been placed in this column as it is. Node 5 is far away from node 1, and that's why it has been replaced, shown by a distance or hop count infinity. Similarly for node 6. Now for the next iteration, which is normally called as the first iteration, we have to find out which is the least count present in the previous step. Here we will find 2 as the least hop count, which is related with the node 3. So that node gets added over here. So node 1 is added along with the node 3, and that distance will be kept common throughout now. So this 2 remains as it is throughout. See, so this is the list count present. Now we have to find out the distance of the remaining nodes with respect to now node 3. So uh, node 3. So let us see how it will be for node 2. Node 2 is away from node 1 with the hop count 3. If you move through node 3, it will be indirectly connected. See why? Because node 1 to node 3, then node 3 to node 4, and then node 2. So it will increase the hop count, and that's why this 3 remains as it is for node 2. Now we will find distance from node 1 to node 4 through node 3. So it will be 1 to 3, 1 through 3 to 4. It will be totally 4. 2 plus 2, 4 hop count. Whereas node 4 is directly connected to node 1 with the hop count 5. Now this hop count is less than this hop count, so it has been changed. Previous hop count was 5, now this is the shortest route with the least hop count or least distance to travel from node 1 to node 4. So this will be the least hop count, and that's why 5 has been replaced by 4. Now node 5 through node 3, again it is far away, and that's why it is indirectly connected, and hence the infinity remains as it is. Node 6 is now directly connected to node 3, so node 6 distance from node 1 will be 2 plus 1, 3 hop count through node 3. So these circled entries have been changed with respect to the previous state. Similarly, we will go for the next step. Now for first iteration, which is the next list hop count, now it is 3. After 2 it is 3. So we have to find out with this list hop count the rest distances. Now 3 is doubled over here for node 2 as well as node 6. So priority will be given to the node 2, because with numbers it is coming first, node 2 and then node 6. That's why. So 2 will be added over here. Now for this iteration, let us see what will be the condition. Now we have to find out distance from node 1 to all other nodes through node 2. Okay, so since node 2 is directly connected, this 3 will remain as it is, and it is common now throughout the this particular steps. Then node 3, as we have already seen, it is directly connected and with the list count, so 2 remains as it is. Node 4, through node 3 it is having 4 hop count. Now we will see through node 2 what will be the hop count. Through node 2 to node 4 from 1, it will be again 3 plus 1, 4. So you may consider this one or this one. So 4 remains as it is. Now node 5 is directly connected to node 2. And that's why now node 1 can send the packet through node 2 to node 5 with the hop count 4 plus 3, 7. So infinity will get replaced by 7. So this is encircled since it is changed. Now node 6, through node 2 it will be 3 plus 4 plus 2, 9. Whereas through node 3 it is 2 plus 1, 3. So list count will be 3, that's why it will remain as it is. Actually comparison occurs, which is the list that has been that is remaining as it is. Now this iteration is over. Now next list hop count after 3 is 4. So now node 4 one another is also present, that is 3, similar hop count. We have to consider D6 also. So 6 has been added over here in the next iteration. With respect to 6, now we have to count the distance from node 1 to all other nodes. Since 2 is directly connected, 3 remains as it is. 3 is directly connected with list count, 2 remains as it is. 4, with the previous hop count or iteration, it is minimum. Why? Because if you go through 6, it is the long distance communication, so it is better to keep 4 as it is. Now node 5 is having hop count 7 in a previous step. Now if you go through node 6, how much will be the distance? Let us see. Now 1, through node 3 6, it will be 2 plus 1 plus 2, 5, whereas previous hop count was 7. Why? Because it was through node 2. 3 plus 4 plus 2, no, sorry, it was through 2 to 5, it was 4 plus 3 7, whereas now from 6, okay, 1 3 6 to 5, it is 2 plus 2 plus 1, 5. So 5 is least than 7, and that's why this entry has been changed. Okay, for d6, 2 plus node 6, 2 plus 1 3 will be the list count as it is. This iteration is over with the change in a node 5 with the hop count, new hop count 5. Now for the next, 3 was the previous hop count. Now next will be the 4. Now related node will be d4, so that fourth node has been added, and now we have to find out the concerned distances with respect to node 4. 2 3 directly connected, so 3 2 remains as it is. Node 4 was having list count 4. Anyway, this is the minimum hop count, that's why we will keep it as it is, 4. Now it will remain as it is. Node 5 through 4, it may have a 2 plus 2 plus 3, it increases than the previous hop count, so this will be the list hop count, 2 plus 2 plus 1, 5. So 5 remains as it is. For node 6, again 2 plus 1, this will be the list hop count, it will remain as it is. So we have considered 4. Now the next list hop count will be 5, and the related node is 5, that has been added in the last iteration, 5. This has been common, remaining same. This will remain same. 4 will remain same. Now 5, this is the minimum hop count which is present by any way, that's why this will remain as it is, and this was remaining as it is from step number or iteration number 3. So this is the final answer with which we can plot the graph. Now this we can represent in a graphical way like this. Node 1 to node 2 with the hop count 3. Node 1 to node 2 with the hop count 3. Node 1 to node 3 with the hop count 2 directly connected. Node 1 to node 4 with the list hop count 4. Okay, so 2 plus 2 4. Then for node 1 to node 5, list hop count is 5. 2 plus 1 plus 2 5, and node 6 list hop count is 6, so 2 plus 1 6. So this is the final answer of the Dijikstras algorithm.